is one thing. It can be also, malfunctioning sensor itself. Right?
Yeah.
So that's what this, when we say the accuracy of the information, it's based on measurements that are done in the past based on what real-time information is given and what is actually measured. Based on that, the number of instances where we are within the state or we are not within the state is how we come up with that problem. Yeah. So what we're saying is that's the best estimate based on real data that we have. Now, if that is systematically observed, of course, then we can factor for that as well. But it's simply based on the data that's available.
So you want QA to be high?
So we want QA to be, so QA here is, if let's say QA was the one where if the real-time data was in a state, we want the actual one, so we want it to be as high as possible, right? So, yeah. So, ideally that's the case, but if it's not, and that's where, it affects the quality of the information, and that's what we are trying to use here, and that's what is being used to either increase or decrease the weight. So it's what we're trying to do, I guess, is we're trying to use data that we can actually collect to come up with these. Now, so that's for how the model is performing based on real data. Then what we tested was how this performs, this model itself performs under different, say, time delays or significance levels. And we use the root mean square error. So the root mean square error here, we use the actual travel time and the mean of the fused data. And the first thing to note is information accuracy dominates everything else. And that's not surprising to see. If you get good information, we weigh that more. If you get bad information, time delay in itself, it really depends on to what extent the time delay is significantly affecting the dynamic nature of travel times. Okay, so in this particular set of tests that we did, we'll note that the information accuracy dominates the effect. Essentially what it's saying is, in order for the time delay effect to be visible in a sensitivity analysis, you have to go to very high levels of information accuracy. So here, information accuracy, we're talking 0.6 to 0.8, whereas here they're lower. What you'll notice is, at this point, you don't see the effect of time delay. Here, you start seeing the effect of time delay where your information fusion model will start capturing that effect here. So you'll see that actually shifting down. Here you have the historical one, the one here. Then the others represent the effect of the shift that needs to be captured because there are time delays. Here, because you have even higher accuracy, you're capturing the time delay effect even faster. The next thing, same thing also for sensitivity analysis. You would expect that as if you have more highest level of significance, you would have better performance, and you'll see that. Except that again here, you'll see that when you have higher level of information accuracy as well, you'll start seeing the effect of that here. On the lower levels, you don't. The information accuracy effect dominates. So we wanted to build an information fusion model that is representative in terms of accuracy, consistency, and robustness. These were the three performance criteria measures that we used. And we wanted it to be able to shield the effects of bad information, so that's why it's adaptive. So every time you have instance of travel time, you update it using the adaptive model, and which means the weights get determined based on that optimization model. Then the key point to note is the short-term travel time distribution may not have a mean, which is close to the actual travel time due to the update process, because we are trying to focus on the distribution itself. And it's reflective of the effects of multiple instances rather than any single instance. Then information fusion performance is dominated by information accuracy. That's exactly what I just discussed. And another thing to note is that the key point, of course, to note is that the long-term distribution is not a good representative of the short-term distribution in terms of linked travel time performance. And these distributions can be used for multiple application contexts. In terms of some of the future work, we want to test this on field data. We have enough field data from the Chicago area, and so we are actually in the process of doing that. We wanted to differentiate the real-time information by vehicle class, actually. So we thought that's something that can make a difference, because we have trucks versus non-trucks and so on. Again here, that can make a difference. Then, if you recollect, in terms of the fusion, we try to fuse a discrete distribution and a travel time range. Can we use two distributions by also using real-time information as a discrete distribution? That would be,
You would need multiple
yes,
observations.
observations of that,
information.
exactly. Multiple observations of the probabilities of the states, and then count with the distribution. Yeah. So, and so, oops, sorry. I also wanted to acknowledge my co-conspirators in this, Dr. Lily Du, who is a postdoctoral research associate, and Dr. Yong Hoon Kim, who is a PhD student. Both of them contributed substantially to this work. And this is, as we speak, we are getting the, what is that called, doc or something like that, the
Yeah.
identification, yeah, for putting it on the internet. So this is in press right now at Transportation Research Project. I also wanted to show one more slide actually before we go to this. There's one other slide that we had, if there was interest. So I already talked about it being a concave objective function, linear, NP-hard. We solved it on GAMS solver. This is our computing environment, and it took about 0.05 seconds to execute each instance for the 19 link A. And I think with that I have all the. Yeah.
Can you give us some intuition about why it's not normally distributed?
Which one? The
travel times.
I mean, I have to be careful. Are we talking about the travel time in the short term or in the long term? I guess.
Is either normally distributed?
The long-term one, some people, have shown, log normal. Some have shown, or in some cases they've shown normal distribution. But coming to the short-term one, the reason why the short-term one wouldn't is because of the dynamic conditions. So, there'll be instances where you'll have. So when I say, dynamic, when we talk about the distribution, we are talking about it representing, a near-term period rather than something that's looking at it for a long period of time. And
that's transient behavior.
Yeah, there is transient behavior there. So that's the key actually.
I still would expect a little bit more normal distribution.
What I would say is it really depends on.
Because when you showed those four, none of them were really normal. They were like, really.
And this is one example of a link. And it really, what I would say is, it is, this is a representation of the spatiotemporal effects of a dynamic network. That's essentially what it's showing. So different links will have different elements. In some links, you will also have, spillbacks and so on. So you can have multiple types of effects. So this is just one this is just one link where we're showing that.
The reason why I'm asking this question is because I was wondering whether, why you chose to discretize with the intervals rather than using a continuous distribution. And maybe, when you get the interval information, can you modify the continuous distribution by maybe like maximizing the probability that, it'll fall in that interval?
Oh, okay. For now, see, so the future work, that's like, what we want to do is we want to, I guess, concatenate the two distributions at some point.
Yeah.
But for now, the reason why we did that was we said that, if you look at a specific link, and we are getting, link travel time information. So we said we may have multiple vehicles from which we have instantaneous reads out there, and we'll have a range. That's essentially the reason why we use that for now. But when we looked at this, we said, okay, now if we can get multiple instances of that, we can try to actually even just use the distributions there. So
here I'm showing a case where you have one real-time information source. So if you have multiple sources of real-time information, how would you extend this? Is it a matter of introducing more weight variables or?
yeah, so this process can be directly extended. In fact, the paper at the end we say that it can directly be generalized to if you have multiple sources of information, because here what you're right, what we're looking at is one source of real-time information. So instead now we'll have multiple sources. So we can extend the procedure itself. If you look at the process that we proposed, that can be extended seamlessly actually. So you're right, and it can be done with this.
But you would be waiting.
Yes, yes.
Sources.
So what it'll do is it'll to some extent, of course, it'll make it a little more complex because
it's
the
not
way steps,
straightforward,
it's not straightforward. But what it'll do is you'll have more access there, and then so you'll also need a lot more data to have the same level of confidence and all that. So one of the interesting questions is if you have some data sources different data sources which have different levels of accuracy to start with, and different frequencies at which data is obtained. That can lead to, very interesting.
Different types of information.
Different types of information. How do you, and one of the questions is how do you take information which is in different formats and trying to come up with a standardized one as well.
What is an interval data?
Yeah. So, yeah.
If in the example, or the numerical example, you had the history starting at the 50, or you collected history for the first 50 days, and then you were projecting for the next 5 days. If you were to change the...
So what we did is, I have to be careful, we're projecting it for within day.
Right.
Right.
But if you say started with, say, 25 days of history,
Right.
and then you compared the 51st days
Right.
distributions, do you see the same kind of stability, or was it more impressed by the next 25 days?
So one of the things, which I've been interested in related to this is, if you go back to, historically if you go back, does it make more sense to use a limited past history to do it? I mean, it's mostly in terms of the level of representativeness. I mean, if your network has changed significantly from the demand-supply perspectives, of course I would expect to see that, right? So one of the things, I'm not sure, I have to go back and check what experiments we did in that context. But that was exactly one of the questions that was of interest to me. And the way we said it, actually in the paper, what we say is, part of it is, if conditions change over time, in about 2-year period, even if there is a new road that comes up, that may change the dynamic conditions as well, right? So that may not make past history as representative as something that's there for the last, say, month, 2 months, maybe, I don't know. So, as and when you have more representative past history, that can be a better starting point, for sure.
Any other thoughts or questions? Yes.
So right now you're assuming that drivers don't get to see any of your compiled information. If there is a situation where drivers, knowing the probability that they'll take forever on a road, would that create, or what kind of a feedback would that create?
That would be an excellent, a lot of my, a lot of my academic life has been in trying to address how drivers behave. In terms of if you provide this as part of your real-time information, that can have very interesting behaviors, because anytime you start putting the information accuracy of this information, I'm giving you information with this accuracy, people will start getting paranoid. Right? That's the first starting point. So one of the things we are actually doing is we're getting a driving simulator soon, and this will be one of the interesting questions to study, where if we do this, my feeling is the more information you provide people, some people get stressed out more. So one of the problems we are studying right now is, are there psychological effects beyond just the fact that you give information and people think they're saving information or not. People may be more stressed or less stressed depending on how they perceive this information. If you give that additional information that the accuracy is this or not, some people say, hey, am I doing it right, am I not doing it, but they're driving at the same time, right? So a very interesting question is giving information, does it have benefits or disbenefits beyond just the travel time savings or loss of savings? You see what I'm saying? Does it affect them psychologically as well? Are there psychological effects that really can be gleaned out? That's actually a PhD study that we're doing right now. But that would be a very interesting question. What happens if you give more information, and information which, anytime you introduce probabilities and so on, you're talking about people wondering. People want very crisp information. I remember, just to go, one step lower in terms of the level of sophistication of information given. I remember at one point I had this rosy picture that we could provide information, based on this dynamic, whatever it is, models to different types of vehicles. But Indiana Department of Transportation wouldn't even come anywhere close to that, because one of the things they talk about is they'll get potentially sued. And the reason for that, if you have big trucks versus small cars, you tell, this is the best route that you can take currently. A truck can go on that and get stuck somewhere in a road where it doesn't have good geometrics. Right there, INDOT will be paying money to that agency out there. So this is even at a much lower level. So there's some very fascinating issues that come up in trying to address such problems. The key point, what I was trying to make was, these distributions will start to act as starting points to come up with more robust methods, more robust sets of information that will provide, rather than providing this directly. If you do this, it may be information, what is that? In some ways, it may be a subset of information that may be too much to process by the driver.
All right, with that, thank you very much.